Hello, students, and welcome to today's, which is kind of like the last free response practice that we're going to have here. Uh, our goal today is to work through this practice. We're going to go ahead and take a look at the test first. And the reason that I recommend that you take a look at the test first is that this test is going to test you on a whole variety of topics, and some you guys know that you know better than anything else. Also, some of the questions are easier than others, and I'd recommend going through and answering those questions first. Once I've kind of gone through and determined which questions I want to make sure that I answer first, I'm then going to go ahead and go through and pick which ones I think are going to be the easiest ones, and that's going to help me to go through the process to answer and get as many points as possible. And remember, our main goal isn't to necessarily answer every question right. It would be nice if we could, but our main goal is to get as many points as possible. So we're going to take a look at our test here, okay? And this first test is asking about gallium, and it looks like it's talking about subatomic particles, okay? First question's all about gallium. It looks like it's asking us to go ahead and use isotopes and explain isotopes. And I know right away that this first section in question is going to be one that I'm going to want to answer every single one really quickly. Okay, so I'm going to look through all of this and I'm saying, all right, question 1, I'm going to answer that one really quickly. Question 2, it looks like it's talking about oxidation reduction numbers. Okay, I know oxidation reduction numbers are going to be a little bit harder than question 1. Okay, so I'm going to go ahead and be like, all right, I'll get question 1 out of the way, then question 2 looks pretty good, okay? Because it's saying oxidation numbers, and I'm like, all right, I got that, okay? I know what to do there, and it looks like this section also has some math, okay? And we could tell that it has this math section right here. And we know that we can do this math, but we know that we might want to save it until it's towards the end so that we can get as many points as possible. Okay, this next one is talking about enthalpy of reaction, change of formation. So this is a thermochemistry section, okay? So I'm going to want to wait till my thermochemistry section until a little bit later. But I'll go ahead and take a look and say, okay, well, which questions are probably going to be easy that I can answer right away? All right. And this one here, it says this one doesn't react at normal temperatures. Okay, I can explain that easily. Like, we know that if it's not working at temperatures, it's going to be that it doesn't have enough energy to, go over activation energy. And since nitrogen's involved, I'll talk about the triple bond. Okay. This one, I can also put an answer for that one. Okay. So some of these that are really simple, I'll go ahead and go through after I'm looking through and answer the ones that I know are really simple. Okay, this one here, also, it looks like this is a bonding section right here. Okay, so if I'm really good at bonding, I'm going to think, okay, let's do number 4. But I know this one, why is it a Bronsted-Lowry base? Okay, well, I can answer that right away. Okay. Reasons why things are put into soils, man, I can answer a whole bunch of these questions without any actual thought. Here, this one, we got some organic compounds. I'm going to be ready when it's time to do the organic chemistry test. If this is a section that you've really, really studied hard for and you feel like it's on the tip of your tongue, answer the quick ones that you can and then go for that one, okay? I know that when I'm going through this particular test, I feel like I have my organic stuff right at the tip of my brain, so that'll be the thing that I'm going to tackle first. So right away, I know I'm going to tackle 5 first just because it's the organic stuff, okay? And it looks like 6 also is having us work with more organics, okay? So what I'm going to go ahead and go through, I'm going to go and take a look at, I've looked at all the tests, I've determined where I'm going to start, and then we go and we fill out all the individual questions, okay, that are really, really easy. Any of the ones we think on, we're going to wait just a second. We'll fill out the easy questions first. Then we'll pick out which section we feel like we had to study the most on, okay, that we have just barely in our brain, and we'll do our information dump on that. So here for question 5, this is the one that I want to go ahead and start on because the organic stuff is fresh in my brain, okay? And it says for question 5, for this one, list which of these species reacts with ethane, okay? Ethane is an alkane, and the only thing that reacts with alkane is a chlorine free radical, okay? And we went over this one. This was how we did an addition or a substitution with an alkane. Okay, so 5(1), that's going to be chlorine. Okay, so that's chlorine. Next, from the list, identify 2 species which can attack the pi bond in ethene. Okay, so now it's talking about not an alkene, but an alkene. Okay, and an alkene, we know that we can add hydrogen halides to it, and we know that we can also add steam to it. Okay, and we can make an alcohol. So that means for part 2, it'll end up being HCl and H2O. Next, from the list, identify a species which can be used to distinguish between solutions of propanoic acid and propan-1-ol. Describe any relative observations. Okay, so I would have to take a look here and see which ones are going to react in a way that I can tell for sure. Okay, and to be honest, none of them strike themselves out to me really easily, except for the carbonate here. And the reason that the carbonate does is because that I remember that, hey, all of our carbonates, okay, when they reacted with an acid, they ended up making CO2 plus H2O, and then some salt. If it's making CO2, well, that's going to be a gas. And if I react in an organic compound and it makes a gas, that's going to be something that I notice. So we're going to put CO2 as our answer, and then we're going to go ahead and say that it evolves a gas. Or we can also say that it's effervescent. Okay? So we've answered 1, 2, 3, 4. 4 points already. Bam! Gonna rock out this test. Okay, B, chlorine gas, okay, and it's looking like it's that free radical chlorine, can be made from Cl2. Under what conditions? Describe the conditions for this process. Okay, well, for B, we know that this is a sunlight or UV light. Okay, so sunlight / UV light. Okay, obviously make it so that your UV looks like a V instead of 2 U's. Okay, and to describe this process. All right, so this is our terms. Okay, this is our homolytic fission. Okay. Name an organic functional group which reacts with a nucleophile in an addition reaction. Okay? So we're looking for some type of functional group which can act as a nucleophile. Okay? So that means that it'll want to grab onto a nucleus in an addition reaction. Okay? And the thing that I'm going to be thinking of, this is something that's wanting to grab onto a nucleus. So it's going to have to be something that has a lot of pull on it. Okay? And I'm immediately thinking right here, things that have pull are going to be our oxygens. Okay? And our oxygens are always going to be pulling electrons away from the carbon. Okay? Or we'll have a high electron density. Okay? So I'm thinking here that it's going to end up being something with oxygen. Okay? And so in general, when I think of something that's reactive with oxygen, I'm going to go ahead and say that it's going to be either a ketone or it's going to be a aldehyde. And if I want to state both, I'll go ahead and write a carbonyl. Okay. So I'm going to write carbonyl mainly because I recognize that a nucleophile is something that's looking for something with a positive charge. It wants to bond to a nucleus. And the electron density is towards the oxygen here. Okay. Next for 3, part 2. Name an organic functional group which tends to react with a nucleophile in an SN1 substitution mechanism. Okay? All right. So it's trying to get us to say, hey, what's going to be one of our best nucleophiles? Okay? And what's going to work in an SN1 reaction? All right? And so I have to think, like, okay, what's going to be the best of the nucleophiles? And in this case, the best of the nucleophiles is often going to end up being a haloalkane. Okay? And a haloalkane is going to work on this one mainly because it's going to be able to pull onto that electron a little bit better. And it's going to stable it. So that's why I'm going to go ahead and say haloalkane. And I'm going to remember here that also it's going to be a little bit dependent upon which carbon it is. So if it's one like this, a tertiary one, that's going to be an example of a great one that we can go ahead and have an SN1 reaction with. Because it'll be able to, this carbon will be able to hold on to that positive charge a little bit better. Okay. And so these are the first 3 questions here. Okay. And we'll go ahead and look for D now. D here is asking us to go ahead and take a look at but1-ene. Okay, so but1-ene, right away I'm thinking about that double bond, and I'm thinking about, man, that double bond is fragile. Okay, I bet something's going to happen there. And it reacts with steam, okay, in the presence of concentrated phosphoric acid. All right, I know. I already know. I said it before that we could talk about steam. That's how we add to a ethene molecule. Okay, to form the molecule, and it's this one. Okay, C4H10O. Each reaction occurs via an intermediate ion. So I gotta watch out. Okay. Because I know that we can end up having 2 different kinds, but it wants to make an intermediate ion. Intermediate ion. So I'm thinking ion here, ion here. So let's take a look. But1-ene is here. When we draw it, we'll go ahead and draw it like this. And we know that it says that it makes 2. Okay. So that means that we're going to end up having a state where we're going to have an alcohol here or an alcohol here. And we know that that's going to happen when this bond breaks. Okay. And when this bond breaks, it's going to either break and give the electron to this side, which will automatically grab onto a hydrogen, or it'll break to this side right here. Okay. Which means that we're going to have a case where for a brief second, we're going to have an ion where this will have a positive charge or this one. Okay. And it wants us to draw those out. Okay. So that means that for this one, our intermediate charge will be here. And for this one, our intermediate charge is going to be on the other carbon. Okay. And then this will go ahead and bond up in there. Next, it says that it wants us to circle the more stable intermediate ion. Okay? It wants us to draw the more stable intermediate ion. Okay? And this one right here is going to be the more stable one. Okay? We know that because it has more carbon. So we'll go ahead and circle this one right here. Okay? And it says to explain our answer, we can't forget this is what's called carbocation stability. It can spread that positive charge to the other ones. Okay? So that's question 5. Okay? And question 5, you should have been able to answer a good chunk of those on your own. Okay? Next, what we'll do, I'm going to go ahead and put the number 6 on the board here because we'll work on number 6. Okay? Working on number 6, going through everything with number 6 here. Okay? All right. So we'll look through it. 2-methyl-but-1-ene reacts with acidified manganate ions. Bam! I'm thinking right away. Acidified manganate ions. We got some oxidation going on here. You can't trick me. You can't tell me that this is not potassium permanganate. Okay? I know what you're doing. I know what your life is about. Okay? We're going to have some oxidation here. Under specific conditions to produce X and Y. Okay? And it looks like Y here looks to be some sort of ketone. And X is questionable. But it makes CO2. So I'm thinking, what makes CO2? X immediately reacts again to form carbon dioxide and water. What has the structural formula? Or Y has this structural formula right here. Okay. First, draw the skeletal formula for 2-methyl-but-1-ene. Man, this is our jam. So, we got but, so 1, 2, 3. 1, 2, 3, 4. We got but1. Okay. But1-ene, which means that we got a double bond on the first one. And we have a second methyl group on this one. All right. Bam. We got our drawing. Okay. We already know we got our points. Why? Because we're confident. Confident in ourselves. We got it. Part B. State specific conditions for acidified manganate ions to react in this way. All right. I know that if we have a lot of reaction going on, we have a lot of energy, and it's probably concentrated. Okay? Hot, concentrated potassium permanganate. That's what's going on. Hot and concentrated. So for part B, hot and concentrated. We haven't even had to think about the reaction yet, okay? It's just asking us things that we know. Things that make sense to us. Okay? Next, B, part 2. Name the reaction type occurring to the functional group in 2-methylbutene in the reaction. Really? Really? You're asking that question? We got manganate going on. We're literally adding oxygens, okay? It's oxidation, okay? Literally adding oxygens. Too easy, too easy. I know what you're thinking, Mr. Valley, this is too easy. And I'm like, yes, this is a random test. All of it's too easy. Too easy. We got this. Draw the structural formula of X. Okay. So now wait. What happened here? Okay. What happened? Earlier, we have this right here. And we know that this bond is going to break. Okay. We know that this bond breaks. Why? It's fragile. It's fragile. Delicate little flower. Okay? It's fragile. So that means that this carbon's going to be lopped off. This one's going to be right here. Luckily, that one has some friends that's helping it out. Okay? It's concerned with this one. Okay? So that means that we got a single carbon. And what happens to those carbons when they're in solution like that? Well, first they make an aldehyde. Okay, but this aldehyde doesn't last very long, and then it goes to a carboxylic acid. Okay, and that's what it's asking what X is. Because this aldehyde, if you have an aldehyde that's like this, or any aldehyde, and it's in hot, concentrated solution, it's going to automatically oxidize again. Okay, so this is what our answer is for number 3, part 1. Okay. Okay. Describe a chemical test and the expected observations to confirm the carbonyl functional group in Y. Okay. So we're looking to see if we have a double bonded O. We're not looking to see if we have an aldehyde or a ketone. We're looking for a double bonded O. Double bonded O's, that's when we're going to use the 2,4-DNPH. Okay. So that's our 2,4-DNPH. And that's going to end up giving us an orange precipitate. Okay, and we watched the video. This one, specific, that's that orange solution. When it bonds in with the carbonyl, it turns into a precipitate. Okay. Next, E. Oh man, E, we got an infrared spectrum. Okay. And it's saying 2 differences between Y and butene. Okay. So 2 differences between these, okay? And it's asking for us only to be concerned about the spectrum above 1500, okay? So what I would like to think here is, hey, we have essentially this molecule and this one. Okay, we know that this is going to be about 1700. Okay, And if you don't know that it's going to be at 1700, that's okay, because there's going to be a thing in your you're going to have a cheat sheet that'll tell you the relative infrared spectra for different compounds. Okay. So we know that a carbonyl, a carbon double bonded oxygen's going to show up with a long line at 1700 centimeters. Okay. We know it. We know it. This one is not going to have that. The other thing that we know, okay, is that we're going to have some weird stretching with the hydrogens here. Okay. So we can go ahead and state that there's going to be some weird stretching between the hydrogen stretching in the ethene that won't show up specifically in the shoot, brain is falling apart, turning into mush. That's not going to show up in the methylbutene. Okay. All right. And this is 2 points. Okay. So we're going to get our 2 points for that. Okay. Maybe we'll get 1 point. I know that I'm concerned more with that one line. I know I can get that point. Next, it's talking about propanoic acid. Oh man. Propanoic acid is reduced by lithium aluminum hydrate. Okay. And it wants us to use an equation to go ahead and show this. Okay. So now I have to think. Earlier, we oxidized things to make propanoic acids or to make carboxylic acids. Here, we're reducing it. So that means that it has to go the other way. Okay? And we know that when we reduce this down, we're not adding any other carbons, so we can't make it go to an ethene, but we can reduce it down to the most that we can. Okay? And the most that we can is that we can reduce it down to an alcohol. Okay? So, our thing, we're going to go ahead and reduce it down into an alcohol. This is our current formula. We're going to put the H inside. And we're going to take this and turn it into an alcohol. Okay, so notice we took one oxygen away because we can't have two oxygens on there, and then we had to put more hydrogens on the carbon. And then we're going to have some leftover oxygen and some hydrogen. Okay, so that's how we would reduce it down. Next, write the organic product form in this reaction, or name. Okay, well, naming. Okay, 1, 2, 3 carbons. We have an alcohol group on the first one. This is going to be propane. One all. Okay, this is for F. And then G. Let's take a look at G. State the molecular formula of W. Okay, molecular formulas, literally counting how many of each type it is. Okay, I didn't even read this part, to be honest. But organic compound W is an ester, which is a structural isomer of propanoic acid. Okay? So, we know that W is going to have the same amount of stuff as this one. Okay? That's what it's saying. It has the same amount of stuff. First question isn't even asking us about esters. It's saying, okay, it has the same structural it has the same molecular formula as this one. Okay? So we just have to write down how many we got. Okay? Molecular formulas are just how many carbons and everything there are. Okay? So we have 1, 2, 3 carbons, 6 hydrogens, 2 oxygens. So the answer for 1 for G is C3H6O2. Okay? This is an example, just not panicking. Okay? We didn't do a lot of work with esters. That's okay. Name the organic product in this reaction. Oh, wait, sorry. Draw a possible structure of W. Okay? Well, it's an ester. Okay? I know that an ester has this. Oh, sorry. I messed up a little bit. I know that an ester has this. An ester has to have this. Okay? But I'm missing some stuff. I need another carbon. Like, somewhere. Okay? I feel it looks better over here. Okay? And then I'll draw on the H's. Okay? I'm going to make sure 1, 2, 3 carbons, 1, 2, oxygen, 6 hydrogens. Okay? And I'm done. This is a possible structure. Okay? For an ester. Okay? So I know that it's an ester. I'll draw what I know the part of the ester that it has to be and then make sure that I have enough and that everything fits. And that's it. I've answered 6. Okay? I've done a good job and I've answered all of 6. Like, I should feel accomplished now. I've won and I've done all the organic chemistry. I'm an organic chemist. Let's go ahead and go through and let's get some more points. Okay? Because it's not just that we get the points. We want to get as many as we can. Okay? So I decided that 5 and 6, those were the things that were on the top of my head. Now, I'll go ahead and go back up to 1, and I'll see which ones I can answer. Okay? 1A, state with reference to subatomic particles how the isotopes of these two are different. Man, is this ACE chemistry? Is this ACE chemistry? I thought this question would be from last year. Man. So how are isotopes different? Well, this one has less neutrons than this one. So I'm going to be like, oh, well, gallium-69 has 2 less neutrons than gallium-71. Okay? That's all I got to put. It's got the same number of electrons, got the same number of protons, but I've just got to put that it has a different number of neutrons. And bam. Done. State what further information is needed to calculate the relative atomic mass of gallium. Okay? Man, I thought that they were going to make me do like a calculation, figure out the average atomic mass. Okay? So in order for us to figure this out, let's think it through. We know that there's 2 isotopes, but we don't know how much of each there is. So we need to say that, hey, we need the relative percent abundance of each isotope. Okay? Part B, gallium. Gallium and its compounds show similar properties to aluminum and its compounds. All right. Great. Now we're talking about aluminum. Okay? And I'm going to think, what do I know about aluminum? What do I know about its compounds? And does it work for gallium? And in general, the answer is going to be yes. Okay. And it's saying that we make gallium trichloride. Okay? So I'm thinking gallium trichloride, aluminum trichloride. What did those things do? Suggest the type of attraction that exists at 500 degrees C. Okay? So it looks like it's pretty hot between the atoms of gallium trichloride molecule. Okay? So gallium trichloride, gallium's a metalloid. And I know from before that also aluminum, when it was bonded with chlorine, we said that that was a covalent bond. So therefore, this first question for B, I'm going to also go ahead and write covalent bonds. Okay. Next, it says between the gallium trichloride molecules. Okay. And it's saying suggest the type of reaction. So between molecules, that's intermolecular forces. Okay. And so I'm going to take a look, gallium trichloride. I'm going to write London dispersion forces. Why? I'm going to write that for like every problem that's between molecules. London dispersion forces. And then this one has 3 chlorines on it and a gallium. So I'm also going to go ahead and put dipole forces. Okay? And the reason is that I don't remember the exact structure of gallium trichloride, but I'm going to guess that the chlorine's going to make at least a dipole on the molecule somewhere. Or maybe even temporary dipole. Yeah. I know London dispersion for sure. I probably just stick with London dispersion for now. Okay. When gallium trichloride is cooled, a solid of it forms. Okay. Gallium 2,6, chlorine 6. Okay. So, suggest the name of the attraction form between 2 gallium trichloride molecules to form gallium 2,6. Okay. So, this one, unfortunately, this one is a straight memorization. Okay. And we knew that for the aluminum oxides, the only way that they were able to bond correctly was when we ended up having that coordinate and dative bond. Okay? So that's going to be the same thing for gallium chloride if it has the same functions of aluminum, which we're going to have to take a guess that it does. All right. Next, gallium metal reacts rapidly when exposed to air. Okay, this makes sense. Aluminum does too. Suggest an equation to describe the reaction when gallium metal is exposed to air. Okay, now I know right away I'm going to be like, all right. So gallium plus oxygen. And I know that in this case, gallium is in the third column, just like aluminum is. And so it's probably going to go 3 plus, and I know that oxygen's going to be 2 minus. So we crisscross them, and we'll have gallium plus O2 makes gallium oxide 2, 3. We have to balance it out, okay? If we do gallium first, it'll be 2. Then we'll have an issue. We'll have to do 3 and then 2. Then this will turn into 4. So you should have 4 gallium plus 3 O2 makes 2 gallium oxide. Okay. Next here, it gives us a table. And it looks like they're reacting it with hot aqueous hydrochloric acid and sodium hydroxide. Man, they're reacting with both an acid and a base. Oh, wait. We remember, this is one of our terms. Give the name for the type of behavior shown by gallium oxide. This makes it amphoteric. This is the amphoteric behavior. It reacts with both an acid and a base. Okay? So that makes it amphoteric. And we're going to be like, bam! I knew my words. I did a little dance, but you didn't see it. Okay. Next, question number 2. The equation shown describes the reaction which occurs when aqueous potassium iodide. Okay, so I'm thinking, okay, we got aqueous potassium iodide. I'm thinking potassium iodide, man, that's clear. Iodine turns brown. I'm thinking, what do I know about this before we go forward? Okay, and aqueous copper 2 sulfate. All right, aqueous blue. Okay, a white precipitate of copper iodine forms. Alrighty. So we got a precipitate in brown solution of iodine and potassium sulfate. Okay, so it looks like these two are still dissolved in. Okay. Balance the equation and include your state symbols. Okay. Well, in this case, the state symbol for this is going to be aqueous, solid, aqueous. Okay. Then we have to count. We'll have to put a 2 here. Two here, 2 here, 2 here, 4 here. Okay, so you should have 2, 4, 2, 1, 2. Okay, if I'm thinking and doing that quickly, you guys should remember how to balance. I'm not going to go ahead and balance the whole time here because I'm already at a long time for the recording. Okay. Deduce the oxidation number of copper in CuSO4 and CuI. Okay. So copper in CuSO4, well, SO4 has a -2. Has to be bonded, so it's going to be a +2 for copper in CuSO4. Okay. Oxidation number for copper in CuI, well, I has a charge of -1. Therefore, Cu will have a charge of +1. Okay? So, +2, +1. Okay? Describe the type of reaction shown in equation 1a. Okay? Or A1. Well, this is a redox reaction. Okay? Explain your answer in terms of electron transfer. Okay? Well, iodine lost electrons. Okay? This one lost electrons because it had a charge of -1. And copper gained electrons. Okay? And that's all it's looking for. We don't have to think too much about it. We don't have to say like, oh, the copper pulled the electrons off of the iodine. No. Iodine lost electrons. Copper gained your electrons. This is a redox reaction. Reduction oxidation reaction. Okay? Oh, man. B? Oh, gosh. Like, looking right away. I see some math here. It's okay. It's okay. We got the math. Okay? And it's saying that we use 17.43 grams of copper sulfate. And why H2O? By further titration of the reaction products, the student concludes that the total amount of CuSO4 in the sample is 0.892 moles. All right, we know how many moles. Use the data booklet to calculate the value of Y. Okay, and it looks like we get 4 points for this one. And oh man, some of this is easy. First one is mass of this many moles of copper sulfate. Man, you guys have that in the bank. You just have to figure out the molar mass of copper sulfate and multiply. Man, easy peasy lemon squeezy. All right, so we're going to go ahead and take 0.982 moles. 0.982 moles of CuSO4. And it wants us to find the mass, so we're going to put grams on top. And we're going to go ahead and find the molar mass for copper sulfate, which we already know how to do. Okay. We'll go ahead and multiply these two together, and we should end up getting 15.672 of copper sulfate. Grams of copper sulfate, CuSO4. But wait, I'm already thinking, this is my stoichiometry problem. Okay, 1, 2, 3, 4. 4 significant digits. 15.672 grams CuSO4. All right. Then we're going to go ahead and look at part 2. And part 2 is asking the amount of H2O in 17.43 grams. Now, wait a minute. Wait a minute here. This was CuSO4. This was our total amount. Therefore, the total amount of water we have to figure out from here. So 17.43 minus 15.67. Okay? And that number we have to divide by 18. Because that's the molar mass for water. That's going to give us 0.09778 moles of water. Bam! We got this. Okay, so we got that answer too. Next is asking for the value of y. Okay, well, y is a ratio. So this is our moles. This is our moles. This is how many moles of water we got. Comparing those two, that's just about 1. Okay? So therefore, here in this one, the answer is going to end up being 1. Okay? All right. So let's go ahead and move on to question number 3 now. Question number 3 is asking us to go ahead and explain the term enthalpy change of formation. Okay? And it's going to... Okay. And they phrase it weird, but it looks like it's enthalpy of formation that they're looking for. Man, that's weird. Okay. Not gonna lie, they asked this question weird. Okay? I'm saying that it's an enthalpy of formation. And enthalpy of formation is going to be the amount of energy it takes to make 1 mole of a compound from its base elements. Okay? So that's what we mean by enthalpy change in formation. The things that you're looking for is that it's 1 mole of the compound, and then the other point is that it comes from the elements itself. Okay. Next here, it wants us to complete a Hess's cycle to generate the values given, and then to calculate the enthalpy. Okay. So this one right here, what we would have to do is we would have to go ahead and say, all right, for our cycle here, we have 3 NO2 plus H2O. We're going to go to an intermediary state. Okay, an intermediary state. And this intermediary state is going to be where we make N2 plus H2 plus O2. Okay, so all of these are going to be intermediary states. All right, so these are going to be our intermediary states. From here, what we're going to do is we're going to go ahead and go down to our end goal elements. And our end goal elements are going to be the HNO3 and the NO. All right. And we know the amount of energy that it takes to go Oh, we also have to make 2. We know the amount of energy that it takes to go from here to here and from here to here. Okay? And what we're going to do is we're going to go ahead and take the enthalpy of formation of our products. Okay? And those are all going to end up being our regular positive values. So we're going to go ahead and take 2 times the value that it gives us for HNO3 plus the value that it gives us for NO, and subtract from that 3 times NO2, okay? Because this is fake. This is fake news. We're not really going there. Plus the value for H2O. Okay. And we'll go ahead and plug all of those numbers in to get our answer here. Okay, and then our end goal answer that we're going to end up getting is that we're going to get negative 70.9. Okay. All right. Okay, nitrogen and oxygen do not react at normal atmospheric temperatures. Okay, this is one that we went over before really quickly, that the reason that they don't is because nitrogen has that triple bond that keeps it really, really firmly held. And then the second is that we just don't have enough energy to break that bond. Okay. Nitrogen oxides form naturally in the Earth's atmosphere. Okay. So here it said they don't react normally. Here they do react. Okay. The reason is that we have brief moments where we have a lot of energy in the atmosphere, okay? And that's when we have lightning, okay? So lightning is an example of a time when we have enough energy, okay? Nitrogen dioxide acts as a homogeneous catalyst in the oxidation. Explain why NO2 is described as a homogeneous catalyst. And that's going to be because it reacts with the oxygen that's not... Well, that's because it's in the same state as the compounds that are in the air. Okay? It is a gas, and it is helping to oxidize another gas. Okay? So because that's happening, and it's in the same state, that's why we say that it's a homogeneous catalyst. Next, it wants us to go ahead and write the equation for this, okay? And we've seen this equation. We'll get to see it here in just another second here. But this is a case where we have SO2, and it comes together with NO2. And what happens is that it'll end up turning into SO3 plus NO, okay? And then we'll have NO plus half O2, and it'll make NO2. Okay, so this works as a catalyst. This is the reaction that they're looking for how we make the sulfur trioxide right here. And I have that one just off the top of my head, so that might be a memorization one if you're really keen on answering all the nitrogen questions and things like that in the inorganics. That's one to commit to memory there. Basically, SO2 taking in oxygen from the NO2, and then the NO recharging with oxygen. Calcium nitrate reacts with ammonia, carbon dioxide, and water to form a mixture of ammonium nitrate and calcium carbonate. Okay, explain why ammonia is described as a Bronsted-Lowry base. It grabs onto a proton. Okay, It grabs onto a proton. That's all we got to say. The product mixture can then be added to soil. State 2 reasons why this mixture is going to be added to soils. Okay. Well, the first reason is that nitrogen compounds are typically a rate-limiting step. Nitrogen is needed for plants to make proteins. The second reason is that it'll also lower the pH of the soil. Okay. Or the product mixture. No. This one doesn't lower it. It'll raise the pH of the soil. Sorry, that's my bad there, because it ends up acting as a base there. Let's take a look. I'm going to verify here. Neutralizes, so it increases the pH of the soil. I was right and wrong at the same time. Okay, so any type of ammonia compound is going to raise the pH of the soil there for you. Okay, also the rate limiting step. Then it wants us to complete the table and name these shapes. So carbon dioxide, this is going to be a case where we want to go ahead and draw it out. Carbon dioxide, double bond O. These are as far apart away. This is 180 degrees. This is going to end up being linear. Next we have NH3. And NH3 is going to have these falling down, these pushing it down, okay? Which means that we're going to have a bond angle between here. That's going to be, about 107 degrees or so, okay? And this one is known as trigonal planar. Wait, no, trigonal pyramidal. And then the last one is going to be water. Water ends up being bent, and it has a bond angle of 104.5. Okay? That's for our drawing and shapes. And then we get all the way back to 5. Okay? That's going to go ahead and close us out. As you guys can see, even I was starting to get tired there towards the end, and I resorted to pulling up one of the answer keys to give you guys the last answer. Obviously, don't pull out an answer key if it's you guys yourself there. But go ahead and make sure that when you're going through, you answer the questions that you know how to do first, or the ones that are really lightly in your brain first. Then go back and answer the ones that you know the processes for really well after that. You're always trying to get as many points as possible. And lastly, I believe in you. If you're here still studying, I believe in you. And I believe that you can do this. Okay? You guys all have a good one.